So, that is basically what public key cryptography actually does, where the sender and receiver do not share the secret key, but shares the public key which is actually known to everybody, and then private decryption key is known only to the receiver. So, as I was telling, that is something which is absolutely confidential, which no other person should be able to know. If by chance that is compromised, you basically go through the exercise again of completely rebuilding the whole pair of keys. Do not try to have the private key compromise, so I will just change the private key alone, but continue to have my own the previous public key. That does not work, because both of them are actually generated by certain mathematical theorems from one large random prime number. Okay. So, although I say I am generating two different keys, they are not generated in a standalone manner, but they are actually generated from the same source. Okay. So, what is the source? That source is a very large, it is a random, and it is to be a prime number. Okay. So, from this large random prime number, there are certain mathematical theorems that are actually applied, and then I get two different numbers. One number I hold it to my chest, another number I scream outside, right. Whatever I am holding it to me becomes my private key, whatever I am screaming outside becomes the public key for everybody to make use of whenever they want to communicate in a very secure manner to me, right. So, that basically is what is the public key cryptography. So, I have a plain text message, encryption algorithm is using Bob's public key, because this is Alice, she wants to communicate with Bob. So, she knows the Bob's public key, she uses that P on the encryption algorithm with the plain text, I get the cipher text, and then Bob will use the private key which is known only to him on the cipher text, and it will magically generate back the original plain text message. Here, although both the keys are totally different, it will still generate back the original plain text message as long as these two keys satisfy certain mathematical principles, right. So, that is basically how the public key cryptography basically works, right. So, what should be the requirements? I need these two keys, one which is the public key and the private key, such that if I apply both of them one after the other, I still get back the original message. That is the first requirement. The second requirement is, given the public key, because it is something which is publicly known, given the public key, if somebody is very intuitive, very curious, wants to actually try to compute the private key, that should be feasibly impossible, right. So, what is technically referred to as a NP hard? Have you heard of a NP hard problem, right. So, given a public key KB, if somebody wants to be very smart and try to compute the corresponding private key, that should basically be a NP hard problem, which essentially means that it is infeasible to calculate, right. So, the very popular public key encryption algorithm is the RSA algorithm, which we would have heard of in different context and at different points in time by different applications. The RSA actually stands for Rivest, Shamir and Adelson, because these three are the people who contributed towards coming out with this algorithm, right. So, authentication. Now, the next aspect of the security that is actually needing to be done is authentication. So, now what do we mean by authentication is, Bob wants Alice to prove her identity to him. Okay. So, when somebody is trying to talk to me, I first need to convince myself that it is that guy alone who is right now trying to talk to me and not somebody else, right. So, it is not like the social media today, where I can actually have any account, right, and try to communicate, and the other person might feel that okay, it is basically the same person is talking to me, but I could actually have another person's photo, which would essentially convey that this is the guy whom I am talking to, right. So, anybody can create a account with Narendra Modi's photo, that does not mean that he is Narendra Modi, right. So, I need to authenticate. So, how do I go about doing an authentication? So, very basic principle, I just say boss I am so and so, but we already know the problem here, anybody can also announce that I am the same person. So, that is a fundamental problem there. So, the next thing is, I basically try to also have the IP address of that particular user appended to the message, right. So, that is, so what is the failure scenario here? Yeah, so this person can also spoof Ali's IP address and then put the Ali's IP address and then say I am Ali. So, this again has a problem. The next thing is I can actually put the password along with the IP address and then send a message that I am Ali's, and then Bob can send back, okay, I understand that you are the person, and then send it out. So, is there a problem here? What could be a problem here? Correct. No, how can Trudy know the password? Huh? So, you assume for this purpose that Bob has access to Ali's password from a central password database. Let us say he can go and query from an Active Directory kind of a database, right. So, some centralized authentication mechanism. Huh? Okay, any other possibility? Have you heard of something called as a replay attack? So, what exactly happens in a play and store store and play attack or a replay attack is, I said eavesdrop and I say impersonate, right. So, when I eavesdrop, I can also parallelly store the packets that is actually going on, right. So, even if you look at some tool like a Wireshark, you have a mechanism by which you can actually capture all the packets and then dump it into a file locally on your hard disk, right. So, when I store those packets, later on I can replay those packets. So, if I have basically stored the packet of what has actually gone from Alice to Bob in this manner, right, after half an hour I can basically send the same packet to Bob, and Bob will think that, okay, this guy has actually again come back, Alice has again actually come back and she is trying to initiate a conversation with me, right. So, that is that could be the problem here. Now, if I do an encrypted password, again I have the same issue where I can store it and then replay it at a later point in time. Now, for this what is generally used is there is something called as nonce. Now, what is this nonce is, the nonce essentially means that a value is legal only when it is actually used once, okay. So, nonce actually stands for not once. So, the moment I try to get the same value again, Bob can immediately find out that boss somebody is playing fishy here, right. So, I basically have a nonce value also generated, but that basically getting encrypted with the shared secret key to be additionally protective. So, that is the next mechanism that is there for a authentication, right. So, again when I use a symmetric key I have a problem. So, for the encryption of this nonce value I will go ahead and use a public key technique. So, that is the that will be that much more safer as far as the authentication part is concerned, right. So, here again I might be subject to a man in the middle attack where I would be able to have this recorded, but what is going to possibly happen is when this person is going to store and replay it at a later point in time, Bob is going to have that value already received, right, and when he finds that the same value is actually coming in right now, he knows that it is something which is getting replayed after storing, and through that mechanism he will be able to prevent this kind of an attack, right. So, that is basically from the authentication point of view what kind of functionality is there. Then the next thing that is actually required is what is called as a hash function. So, a hash function, have you heard of any kind of hash algorithm till now? SHA, anything else? So, within SHA itself you have different versions. So, you have a SHA1, SHA256, SHA512. So, what is the first algorithm? MD5, right. So, what does basically a hash function actually do is, so hash function is basically a computationally efficient function mapping binary strings of arbitrary length to binary strings of some fixed length. Okay. Now, what I basically tell is, if I have a text, okay, of let us say a string that I want to send it to another party, we said that somebody, one of the possible types of attack is somebody trying to do a modification of the content, right. So, I want to have a mechanism by which the receiver will come to know that boss somebody has modified the data here, okay, and that is what I actually use a hash function for. So, when I have a hash function, right, so there is going to be an algorithm that is there. When I send my entire data that I want to send through that algorithm, he is going to generate me a hash value. Okay. So, when I am sending the message across, I will also send the hash value along with the message, right. Now, when I send the hash value along with the message, what will happen? The other side will receive the entire thing, right. Now, what is it that the other side is expected to do? The other side is actually expected to run the same algorithm, right, on the data that they have received, and if they find out the value that has actually come there and the value that has been received as part of my message to be same. Okay. What does that mean? Message has not been tampered with, right, because the beauty of this hash function is that it is a computationally efficient function mapping binary strings of arbitrary length to binary strings of some fixed length, right. So, when you have a hash function, one of the requirements of the hash function is going to be that if I basically change one bit of my input text, right, and then give the modified text to my hash function, the hash value that this guy is going to generate to me should be as much as possible completely different as compared to my previous hash value, right. So, let us say that I have actually sending a text of 1 2 3 4 5, okay, to the remote side, right. This number 4 has basically become 5. So, somewhere either because of corruption of some memory access, or somebody was actually trying to really play it very smart, he was actually trying to modify that value, whatever it is, out of these 5 numbers only one number has got changed and has actually gone and as a modified string to the other side. What I would essentially want is, when the same hash algorithm is being subjected to with the received text, the hash value that it is generating should not be anywhere closely resembling to whatever I have generated and then sent along with my message, right. So, that is one very important requirement of my hash algorithm, right. So, what we typically call as a avalanche effect. So, we all know avalanches, right. So, the weather disturbance, when it comes really very bad. People will not be able to sustain it, like what very recently we had in Chennai also, right. So, what is that avalanche effect is that if I basically change even one bit of my input text, right, the corresponding number of bits that has to be changed in my hash value should be significantly higher, right. So, if I change one bit alone should not be getting changed in my hash value, in which case I will have a problem in finding out whether there has been actually any modifications on en route or not, right. So, the requirement of an hash algorithm, this actually has this requirement of it having a good avalanche effect, and also that with the hash value being given into the hash algorithm, I should not be able to get back the original message data, right. So, that is basically the reason why the hash functions are typically referred to as a one way function. So, I cannot get the reverse part of it with the hash value input into the hash algorithm, I cannot get the message data. Only when the message data that I want to actually be checked for my integrity is given as an input into my algorithm, I will be able to get a hash value. So, that is basically the reason why we typically refer to as a one way function, right. So, the probability of two messages with the same hash is minimized. So, please note that it is not eliminated, is not used here, it is only minimized, right. So, what we technically call as a collision. So, the idea here is that the number of collisions that could typically happen has to be extremely less, right. So, that is going to be one very important criteria based on which somebody is going to measure the efficiency of the hash algorithm, right. So, we are talking of this as an efficient function here. One of the parameters of efficiency is going to be measured by, is there going to be a collision or is there going to be a good avalanche effect by using this algorithm to generate the hash value, right. So, then the next aspect that you are going to very commonly be getting referred to is what is called as a digital signature, right. So, we all know a normal signature that we do on a piece of paper. Now, what is a digital signature? So, a person has actually sent you some data, okay. So, today he has sent you some data, he has communicated something to you. Tomorrow you do not want him to basically say that, boss, I was never the one who actually sent you the data itself, I do not know who sent it, right. So, most of the politicians today do, na. So, advertently, inadvertently they come out with some statement out of their mouth. Unfortunately, in this world of social media, every single letter, every single word is all recorded, right. Then after some time they have to do a backtrack saying that I never said it, media misquoted me, right, I meant that only, media used wrong words, all those kind of things, right. So, similarly, when you have accepted to a particular message, right, when you have said that, boss, I confirm and I accept and I take this responsibility, whatever it is, tomorrow you should not basically be in a position to say that, boss, somebody has spoofed as me and then sent it, somebody has impersonated as me and then sent it to you, right, that is simply not acceptable, right. So, the digital signature basically helps you to do that. So, sender digitally signs the document establishing he is the document owner or the creator, and then it is verifiable and non forgeable. So, the recipient can prove to someone that Bob was the one who actually has sent this particular document or this particular message, and tomorrow Bob can also not say suddenly that I am not the one who actually had sent it. So, in order to prevent this, you have the digital signature, right. So, there is a message the way that I will use the Bob's private key. This is really the ulta of what I do for an encryption. So, when I actually had to send for my encryption and decryption purpose, what I used to do was I used to use the public key of the recipient, right. Here what I do here is that I use my private key. The moment I use my private key, what will the other guy do? The other guy will use my other guy wants to get back the original message. What will he do? But he does not have my private key. No, please, you have to use my public key, which anyway he knows, correct. Now, what has this got? What has this proved indirectly? How is it proved? Because remember I told you the private key and public key is a pair, okay. So, if it has been encrypted with your private key and somebody uses my public key to decrypt it, they will get only junk, right. But here what is actually happening is Bob is going to be using his private public key, right, and public key, okay, no, so the signed message is going to be actually encrypted with the private key, the other person will basically be using the public key, right. The moment he actually gets back, Alice gets back the original message by using Bob's public key, indirectly it is communicated, it is accepted that Bob only has sent it. Why only Bob has sent it and not Vasan has sent it? Because Bob's private key is known only to Bob. Okay. So, tomorrow with that ciphertext, with that encrypted text, Bob cannot claim that boss, I was not the one who sent it, right. So, in the encryption and the decryption for confidentiality, we actually encrypt with the public key and decrypt with my private key, but when I have to use it as a digital signature, what I do is I do the reverse. So, I encrypt it with my private key, and then when somebody decrypts it, they are going to use my public key, and thereby it basically proves that I have sort of attested whatever the contents of the document or the message or whatever it is, right. So, this is basically the concept of a digital signature. So, there are details on how, as I was telling, that non-repudiation essentially is the one there the Bob cannot later on claim that he had not actually sent the message and not standing by that, right. So, with this I will be able to prove that. Now, message digest is basically a hash function, but computationally expensive basically because when I have a public key encryption that I have to do for very long messages, right. See, the whole process of encryption and decryption is not really very cheap. Okay. So, when we say it is not very cheap, what do we essentially mean here? Time. Time for doing what? Because whether you are running a DES algorithm, whether you are running a RSA algorithm, right. So, DES algorithm for example goes through 16 rounds. Yeah, Care, Anurag, Neelit, any clarifications? Okay, any other groups, any clarifications? Okay. So, essentially when I have to do a encryption or a decryption of a very long message, it is going to take a lot of CPU cycles on that particular encryption and decryption, which I would possibly want to avoid, at least in situations where it is avoidable, right. So, for that what is actually done is a fixed length easy to compute digital fingerprint, which is essentially, as I told you, it is a hash function. So, I get a fixed size message digest and I add that message digest to the large message and then send it out, right. So, in addition, if I want to really make sure that this hash value is also not modified on the way, I just encrypt the hash message alone, hash of that message alone before sending it out to the other party. So, I am not really required to do an encryption of my complete long message because of the message size is long. I am going to end up spending a lot of time on that, but if I basically do an encryption of a smaller hash value and just append that encrypted hash value with my message and then send it out, I will possibly be able to satisfy quite a majority of my requirements. Then I would prefer to do it for saving up some of the CPU cycles which I would otherwise be requiring to be spending on that, right. So, similarly to just how the hash function the primitive hash value is used, I will basically calculate the hash function on both sides and find out whether the hash message that I am getting on the recipient side and the value that I am getting out of the calculation, right. So, this is basically the calculation that I have myself made on the message, and what I have actually got after the decryption part of it. If they are equal, then I will be confirmed that my message had not actually got modified en route. So, instead of actually trying to spend so much of time in trying to calculate my digest value for the entire message, I only calculate the value for a small sized hash value alone and then encrypt it and then send it out, and at the receiving end I do the decryption and then do the comparison, the same comparison that I will do otherwise. If I find it both matching, then I am still convinced that yes, that the message that I have actually right now got is something which is unadulterated, so to say, right. So, MD5, SHA1, SHA256, 512 are the other common hash function algorithms that are typically used. So, you have typically the different RFC documents that are there for each of these algorithms also. So, we understand what is RFC, right? What does RFC stand for? Request for comments, right. So, these are all actually available on IETF. So, you go to ietf.org, that is basically the standardization body for all the internet protocols. Each of the protocols has a corresponding standard document that is basically referred to as the RFC document. So, one protocol will be mapped to multiple RFC documents, typically one or more RFC documents, which will give you the complete details about that particular protocol and what is that, where is it being used, how is the protocol to be implemented, which all the vendors are supposed to follow for their respective implementations, right. So, all these algorithms are actually available as RFC documents that we could actually make use of, right. So, now there is something called as a public key certificate. Now, we talked the primary reason for us to come out with the public key cryptographic algorithm was with a symmetric key. I need to actually be going through the trouble of sharing, right. But in public key cryptography also I am doing the sharing. Okay, I expected at least one of you to ask me the question, sir, in public key cryptography I have to share the public key. So, the same problem is existing here also. Is it the same problem or is it a different problem? In symmetric key cryptography we said it is the same key, because it is the same key used by both sides, we said I have to share the key, and I said that is a problem, right. So, because of that problem we reasoned out saying public key cryptography is the way to go, right. In public key cryptography we said there are two different keys, one key is not shared, only known to me, the other key is shared across to everybody else, right. Now, you should have immediately asked the question.
But without public key, there is not going to be a problem.
Why?
They can only send data to you, they cannot decrypt the data that they want to send.
Okay. So, is that the only reason why it is not a problem? Why is sharing the symmetric key a problem in symmetric key cryptography, but why is sharing a public key is not a problem in asymmetric key cryptography? Both are sharing, no?
Because nobody else can do anything with that public key.
The very nature of it being public, I really do not care whether everybody comes to know of it, right. But what is happening in symmetric key? That is the most important part. If somebody comes to know of that, then whatever messages or data that is going for that particular user or a node is gone, right. So, public key I have got to share. So, how do I share a public key? So, that is where my public key certificates come into play, right. So, I basically have the public key data along with certain information like what is the version of the certificate, who is the issuer. So, there are people called as certificate authority, shortly called as a CA. So, these are all licensed people who can give a public key certificate, right. So, that is the reason why if you go to some websites, okay, let us say it is basically a a site that is actually promoting e-commerce. So, the moment it is a e-commerce site, it will always be only HTTPS, correct, it will not be HTTP. Have you observed the difference? So, what is that S in that HTTPS? Secure. So, when you say HTTPS, what is actually happening? So, if you are very curious, what you should do is you should try to capture packets in Wireshark, right, when you are trying to access your banking site, for example, okay, or Amazon site or whatever, right, and you have to capture packets in Wireshark when you try to access sites with HTTP protocol. Then look at the difference between the two of them, right. When you are captured packets with HTTPS protocol, the content will be completely encrypted, okay, you cannot make head or tail of the content. When you have captured package with HTTP protocol, you can get to know the complete details because it will be in a plain text form, right. So, the encryption is going to happen first from your browser to the server, okay. So, let us say that you are going to icicibank.com, okay, because you want to access your online account, your browser is IE. So, IE, because it is an HTTPS connection, has got to encrypt the content before sending it to the web server of icicibank.com, right. For encrypting the connection, what does it require? Public key of ICICI Bank's web server, right. So, he has to basically get the public key from him. How is he going to get his public key? Using this certificate. Now, anybody can tell somebody else's public key as some other public key, correct na, right. I can go and spoof and say your public key is this to your client, it will become a problem, no, correct. So, somebody has got to authenticate, boss, ICICI's public key is only this, no problem, that person is what is called as a certificate authority, okay. Now, what we do is the certificate authority is actually squeezes extreme amount of money, right. So, a small sized group or an organization cannot afford to pay this kind of a money. So, what they do is they use a OpenSSL kind of a tool set which also generates a certificate and then pushes it into the web server. So, that is the reason why when you go and access certain web servers, certain websites, you might have seen a pop-up box opening up saying that this digital certificate is not signed by a trusted authority. Do you still want to continue? Correct. Why has that happened? Because I have the digital certificate in the form that I have given here, but the signing authority, right, the issuer, all those things are non-recognized fields, right. So, the browser is basically throwing a problem back at you, boss, if you accept it, I will continue. If you just try pressing no there, okay, your connection will not be getting set up, right. So, I am going to use a public key, but I need to ensure the public key is actually the one for whom it is being claimed for and there is no impersonation there. For that I am looking out for somebody to give me a authorized this thing, and in cases where I am not able to buy that kind of a certificate, I have generated myself and then put it into a web server, right, which is not signed certificate, then you will have a pop-up box thrown like this and the browser will basically put the onus on you to decide, right, whether you want to accept it or not. If you find it fishy, you can say no, I do not want to take a risk, right. If you say that yes, I can do it, then it will further go down and then get the public key, I mean get the certificate, extract the public key from there, because you see here this is only the entire certificate, this is the only thing which is related to the public key, everything else is paraphernalia, right. So, it will extract the public key from here, use that public key now for the encryption part, right. So, that is basically where I have to use a public key certificate, okay. So, in summary, we have gone through the high level overview of symmetric and public key cryptography. We have looked at the authentication, we looked at message integrity. Message integrity is basically nothing but my hash function, right. So, and the digital certificate, right. So, now going forward what we are going to do is we are going to look at how these different techniques and algorithms are actually made use of by ARM processor as an example, right. So, what kind of components you have inside, where do you actually make use of each of that, what are the benefits of that, and then I will finally take you through one device that we have actually built with the ARM processor for you to get an idea, right.